Hello everyone, welcome back to my YouTube channel. So for this week, I'm going to explain to you how you should tackle the question from quiz 7. So altogether we have 6 different questions and let's start with the first one. Question number 1. The decomposition of hydrogen peroxide follows the first order reaction. In 50 minutes, the concentration of hydrogen peroxide decreases from 0.5 molar to 0.125 molar in one such decomposition. When the concentration of hydrogen peroxide reaches 0.05 molar, what shall the rate of oxygen be? In order for you to answer this question, you need to understand two different rules. One is the rate law and the other one is the rate expression. So we are going to start with the rate law. According to the question, this reaction follows the first order reaction. So the first thing that you need to do is you need to be able to calculate the value of K, which is the rate constant. So since this is following the first order reaction, we're just going to use the first order reaction formula, which is the ln AT is equivalent to negative KT plus ln A naught. Right, so we're just going to plug in. So ln AT, which is the final concentration, is ln 0.125, equivalent to negative K, and your T is actually 50 minutes. So just write 50 here, plus ln, the initial concentration is 0.5. Right, so it means that you can calculate your K is equivalent to 1.3864 molar divided by 50 minutes. Alright, therefore you get your K is equivalent to 2.7728 times 10 to the power of negative 2 molar per minute. Right, so this is the first step of doing this question. Alright, if you look closely at the question, you can see that what you were asked to calculate is actually the rate of oxygen. Therefore, now you need to do the chemical equation for this reaction so that you can write the rate expression. So it is the decomposition of hydrogen peroxide. So it shall decompose into water and also oxygen gas. Right, so from here you can actually write the rate expression, whereby the rate expression is equivalent to, so whatever in the reactant must be negative. So negative delta concentration of H2O2 delta T equivalent to positive delta concentration of water over delta T equivalent to positive also 1 over 2 concentration of oxygen over delta T. In saying that, we can say that because now the thing that you are going to compare is just hydrogen peroxide and also water. So we are just going to look at this one and this one. So we can say that the rate is actually equivalent to negative delta concentration of hydrogen peroxide over delta T is equivalent to 2 delta oxygen gas delta T. This one you need to just bring this up so you get this. But in the question, you were not asked to calculate 2 delta oxygen gas over delta T. So we are going to manipulate this into the thing that we can use further on. Alright, so since the question asks you to calculate the rate of oxygen instead of 2, so we can say that the rate is actually equivalent to delta O2 over delta T is equivalent to 1 over 2 delta hydrogen peroxide divided by delta T. Right, so we already have this, and we know that the value of K, which is the rate constant, is equivalent to 2.7728 times 10 to the power of negative 2. Right, so what we are going to do now is to merge this into rate law again. So in rate law, we can say that rate is equivalent to K, concentration of any substance. So in saying that, because we know the one that we want to calculate is actually the concentration of the rate for oxygen, whereby the rate of oxygen is equivalent to half concentration of hydrogen peroxide delta T. So this is the rate of hydrogen peroxide, right? So we can say that the rate of oxygen is equivalent to half K, the concentration of hydrogen peroxide. Okay, so now in the question it says that the hydrogen peroxide reaches 0.05 molar. So what shall the rate of oxygen be? So the rate of oxygen can be calculated here. So now we need to plug in this 0.05 molar to the equation, substituting the concentration of hydrogen peroxide. Alright, just a quick recap. So we can see here that the rate is equivalent to delta concentration of oxygen over delta T is equivalent also to half delta concentration of hydrogen peroxide delta T. So it means that the concentration over delta T means that that is the rate. So when we talk about rate and we want to convert it to the rate law, so we want to write it as rate is equivalent to whatever unknown, this, so we have 1 over 2, and then we have K to the substance. Right, so since we know that the value of K we have already calculated just now is equivalent to 2.7728 times 10 to the power of negative 2. So the concentration of hydrogen peroxide given in the question is 0.05. So you can get the rate of oxygen is equivalent to 6.9320 times 10 to the power of negative 4. This is the rate of reaction for this oxygen, the rate of oxygen, because it is actually equivalent to 1 over 2 delta concentration of hydrogen peroxide delta T. So we convert that to the rate law, and then you can get the rate for oxygen gas is actually equivalent to 6.9320 times 10 to the power of negative 4. Let's move on to question number 2. If the rate of formation of ammonia is 0.345 molar per second, what is the rate of disappearance of hydrogen gas given that the reaction goes as follows? So in order for you to answer this question, you need to look at where all the chemicals is being put. So the first one is the reactant, so everything in the reactant should be negative and everything in the product should be positive. Right, now let's write the rate expression. So rate expression is equivalent to rate equivalent to whatever in the reactant should be negative. So negative delta concentration of nitrogen gas over delta T equal to, because you have 3 here, so it's equal to negative 1 over 3 delta concentration of H2 over delta T equals to positive, because this is already product, and then it have 2 here, 1 over 2 delta concentration of NH3 over delta T. Alright, So the next thing that you need to do is look at the question again. It asks you to calculate the rate of disappearance of H2. So you want to calculate this one. When given to you the rate of formation of ammonia, so you already know this one. So in saying that, we can write -1/3 delta H2 delta T is actually equivalent to +1/2 delta and H3 delta T. Alright, so from the question, you know the value of delta and H3 delta T, which is equivalent to 0.345. So you're just going to plug in here so that you can get the value of this one. Alright, so I'm just going to write this again. So -1/3 delta H2 over delta T is equivalent to +1/2 delta and H3 over delta T. Alright, so it is equivalent to +1/2 times this value 0.345. So you shall get 1.7250 times 10 to the power of -1. But the fact is, this one is for -1/3 delta H2 over delta T. But you were asked to calculate delta H2 over delta T. So what you're going to do is you need to bring this 3 up there. So 1.7250 times 10 to the power of -1. So this value times 3. So you should get the value of the rate of disappearance of hydrogen gas is equivalent to 5.1750 times 10 to the power of -1. Right, so another thing that you need to look at is the location of your H2. So because it is at the reactant, so basically we need to have minus over here. So it's going to be, the final answer is -5.1750 times 10 to the power of -1. That is the rate of disappearance of hydrogen gas in this reaction. Question number 3. It took 143 seconds for 50% of a particular substance to decompose. If the initial concentration was 0.060 molar and the decomposition reaction follows the second order kinetics, determine the rate constant of the reaction. Alright, this is a rather straightforward question because given to you is it took 143 seconds, right? For 50%. So it means that this 143 is equivalent to the half-life. So, and then it says here that it follows the second order kinetics. Therefore, the half-life for second order is equivalent to 1 over K times A naught. So, given to you in the question, the half-life is equivalent to 143 and then is equivalent to 1 over K. So the rate constant is the thing that you want to calculate, and given to you the initial concentration is equivalent to 0.060 molar. Alright, so what you need to do is that you just need to bring this up. So it's 143 times 0.060 K is equivalent to 1. Therefore, what you can get is 8.58 K is equivalent to 1. So from here, you can get the value of K is equivalent to 1 divided by 8.58. Therefore, you shall get K is equivalent to 1.1655 times 10 to the power of -1, or you can put it 0.11655. Let's move on to the next question. Calculate the percentage of the material that shall persist after 80 minutes if its half-life is 20 minutes and the reaction follows the first order reaction. Given in the question is the half-life, which is 20 minutes, and it follows the first order reaction. Therefore, we can use this information. So T half is equivalent to ln 2 over K. This is for the first order reaction. So given to you the half-life is 20 minutes, so ln 2 over K. So we can get your K is equivalent to ln 2 divided by 2. So you should get K equivalent to 3.4655 times 10 to the power of negative 2. Right, let's look at the question again. So it asks you to calculate the percentage of the material that shall persist. Means that the question wants you to know what is the percentage of your starting material or your reactant that will be there still after 80 minutes. So what you're going to do is you need to use the first order reaction formula, and then you use the value of K that we have calculated here, and you shall get what is your AT. So ln AT is equivalent to negative KT plus ln A naught. Right, so what is your A naught? Because the only thing that you know here is the T and also your K. So from here we can say that negative 3.4655 times 10 to the power of negative 2, and your T is 80 minutes. Why we don't need to convert 80 minutes to second? Because your half-life is already in 20 minutes, so means that we are calculating the value of K is in minutes as well. So another thing that you need to do is what is your initial concentration. So we assume that initially there's no product being formed, so your reactant is 100%. So 100 divided by 100 is equivalent to 1. So equivalent plus ln 1. So from here, from the calculation, we shall get negative 2.7680 plus 0, because ln 1 is 0. So this is the value for ln AT, but we just want AT, the concentration of AT. So what you need to do is just have to the power of 2.7680. So you shall get 6.2787 times 10 to the power of negative 2. Right. So since it wants you to give the answer in the percentage form, so you need 2 times 100, so you should get 6.2787%. So this is the final answer for this question. Let's move on to question number 5. The rate constant for the first order reaction at 600 Kelvin is 2.2 times 10 to the power of negative 5. What is the percentage of the reactant that shall be decomposed after being heated at 600 Kelvin for 90 minutes? To answer this question, the first thing that you need to look at is what is the information given to you. So the first information given to you is the rate constant, and it is in second. And then you were asked to calculate how much, the percentage of the reactant that shall be decomposed after 90 minutes. So what you are going to do now is you need to match the duration of time with the rate constant given to you. So since your rate constant is in second, so you need to change this 90 minutes to second. So 1 minute is 60 seconds, so 90 times 60 is equivalent to 5400. So this one is already in second. Alright, so another thing that you need to look at is it follows the first order reaction. So you can use the first order reaction formula, which is ln AT equivalent to negative KT plus ln A naught. Right, so your ln AT is the thing that you want to calculate. Given to you is your rate constant, which is 2.2 times 10 to the power of negative 5, and your time is 5400, and the initial concentration. So the initial concentration is the same concept. Initially we assume that the concentration of the reactant is 100%, so 100 divided by 100 equivalent to 1. So therefore you can get negative 1.1880 times 10 to the power of negative 1. So we would not want ln AT, we just want to get the concentration, the final concentration. So AT is equivalent to negative 1.1880 times 10 to the power of negative 1. So you shall get 0.8879. Okay, this is the concentration. Alright, so when we do this, we assume that initially it is at 100%. So 100 divided by 100 equivalent to 1. So initially we have 1. And then after 90 minutes, this is what's left. So minus 0.8879. So you should get 0.1120, but you will ask for the percentage. So to make a percentage, you need 2 times 100. So it becomes, it becomes 11.20%. So this is the final answer for the 5th question. Right, we are now at the last question for quiz 7. In the reaction A to produce a product, it was found that when concentration of A has fallen to half of its initial value, the reaction proceeds at the same rate as its initial rate. Means that the half-life and the initial rate are the same. So is the reaction 0 order, first order, or second order? So this one, because the half-life and then at the initial also is at the same rate, means that the rate is not changing as a function of time. Therefore, we can assume that this should be a 0 order reaction. Alright, so this is the end of this week's video. Thank you very much for watching. I hope that this video will help you to understand more on the topics in chapter 7. So take care and stay safe. Goodbye.